In the previous video lecture, we have discussed what are the internal forces subjected in the beams, that is shear forces and bending moment. It how can be it calculated? So everything we have discussed in detail in the previous video lecture. So here, let us see in this video lecture, that is the topics to be covered in this video lecture or stress distribution due to bending moment, stress distribution due to shearing force, flitched beams and leaf springs. First let us see the stress due to bending. So there is a concept in this case that is called as pure bending. Pure bending means that is bending produces a change of curvature in beams. So shear induces a distortion. Normally we are getting the deflected shape of the curve of a beam. It is elastic curve, so that is curvature of beams. Loaded beams develop both bending moments and shear force. Any beams, if it is loaded, definitely there will be the internal forces of bending moments and shear force. Thus, while deriving expressions for bending stress, only bending moment present and that shear is absent. In that case, we just omit the effect of shearing and we just consider only the effect of bending. We know that dou m by dou x is equal to f, and it is calculated that f is equal to dou m by dou x is equal to 0, and so m is unvarying along this span. So in that case, if there is no shear force, means the m is constant throughout this section. So this state of unvarying bending moment, that is free frame shear, as simple bending or pure bending. So there is a another concept, that is plane sections remaining plane. So let us take a small length of beam here of cross section in this figure 4.2, curvature due to bending. If there is a bending moment m acting on that length, then we would have two moments m acting on section AEC and BED here. Okay, there is a moment and another bending moment. So A dash, E dash, C dash and D dash, F dash, B dash is the bend shape of the beam. You see that A dash, C dash, E dash and B dash, D dash, F dash, D dash, D dash, F dash, D dash, F dash and B dash. So after bending, the profile becomes like this, that is bending profile. In the bending process, AEC becomes A dash, E dash, C dash, BFD moves to B dash, F dash, D dash, and an internal section GH becomes G dash, H dash. You see that there is the internal section G and H, and after bending that section becomes G dash, H dash. In drawing the figure, we have tactily assumed that A dash, E dash, C dash is a straight line, just like AAC. In fact, AAC is the part of plane rectangular section. After the onset of bending deformation, A dash, E dash, C dash remains part of a plane section. In other words, sections of the beam which are plane before bending would remain plane after bending. We have not proved this. We have assumed this. These assumptions would help us get a kinematic relation between curvature and strain. Again, when a beam bends as shown in figure 4.2, we see that one extreme fiber AB elongates, another extreme fiber CD shortens. In between, a fiber EF remains unaltered in its length. It has therefore no strain and no stress. This fiber EF is called the neutral fiber. You see that here. Definitely the C dash D dash has smaller length when it compare its original length of CD, like that. A dash B dash is having a larger span when compared to its original span of AB, but in which there is the another fiber which is having EF dash maybe the same length EF. Okay, so there will not be any stresses subjected on this fiber. So that fibers is called as neutral fiber. So the horizontal plane containing EF is neutral plane. This plane intersects every cross section along the neutral axis. So let us take a cross section of the beam. Let its cross section breadth B and depth D, in which all the sections which crosses this neutral fibers, and therefore it has a neutral axis. So this is curvature due to bending. So the beam element, let us see first strain due to bending. The beam element figure 4.2, let us assume bend such that the neutral planes has a radius of curvature r. It obvious that let it be A dash B dash would have a radius of r plus d by 2. You see that A dash B dash is having a larger span, that is curvature span, and its radius r plus this d by 2, and C dash D dash would have a radius of r minus d by 2. Okay, any fiber G dash H dash at a distance y from neutral axis will have a radius of r plus y. So let this one be the y distance. So we just have fix any fiber, any distance in between these two, this all. The elongation G dash H dash is r plus y into d theta minus r d theta. You see that this A dash B dash force gets more elongation. Suppose let us choose this fiber on this elongated zone, and therefore how much it's elongated. So that thing can be found r plus y into d theta minus r d theta. Okay, so you see that let this angle be the d theta, and therefore so this will be r plus y. This distance is y. Let us take this fiber, and this distance be r plus y. When it is this resolved means, so it becomes r plus y d theta and minus r d theta. That is nothing but the elongation. The fiber gets elongated portions. So which becomes y d theta. The strain in G dash H dash. The strain in G dash H dash be y d theta. The strain in G dash H dash is elongation divided by original length. Therefore y d theta divided by r d theta. This is change in length divided by this is the original span r d theta. Therefore it is y by r. Therefore this is nothing but bending strain epsilon is equal to y by r along this section. We just find the strain along this section. So let us take a section and its distance y from the neutral axis. Now because of this bending effect, now the fibers on these sections also strained. So let us find this strain. So that thing becomes y by epsilon is equal to y by r. This is a kinematic relationship. This is of course valid for all values y from minus d2 to plus d by 2. So stresses due to bending, we get the clue that sigma is equal to, so by knowing strain, when it is multiplied by Young's modulus, we obtain the sigma. Therefore sigma by y is equal to E by r. So this is one equation which is famous equation of simple bending. Now stresses due to bending moment. Now we have determined stresses due to strain, bending strain. After that we are going to see the stresses due to bending moment. So in which the tension produces elongation. To sustain elongation you need a tensile stress. Likewise to bend length of beam we need a bending moment. Conversely, if we apply a bending moment on a length of beam, it bends to a curvature. Herein we will try to relate bending moment m and the resulting curvature becomes 1 by r. You see that we have a length of beam equal to r theta. It bends to a radius r due to bending moment m. The strain at any distance y from the neutral axis, so it was already found, epsilon is equal to y by r and sigma is equal to e y by r. Okay, that is E into epsilon. We find that stresses are compressive below the neutral axis and the tensile above the neutral axis. In case of, if we find that stresses are compressive below the neutral axis and the tensile above the neutral axis. For the case of hogging bending nature, the tensile stresses sum up to a net force T and the compressive forces stresses sum up to an equal and opposite forces C is equal to T. The moment of the couple T C should be balanced net moment M on this section. Therefore 0 to d by 2, which is equal to sigma into b dy. Therefore M is equal to 0 to d by 2. Sigma is nothing but that strain into young small as y by r into E. And for this particular splice on the given cross section, that is b into dy. So this is nothing but moment. Okay, moment. That means stress into area, which becomes force, and it should we are finding the moment at that particular fiber with respect to neutral axis, that is the distance by. So force into distance, which becomes the moment, and this moment varies from 0 at neutral axis to d by 2, that is the maximum at that fiber. So because the maximum bending stress at that extreme level, and therefore for the given section E young smallest is constant, and for the subjected bending moment there will be the constant radius of curvature area 1 by r, and therefore 0 is equal to E by r, 0 to d by 2, these two are constant. Let us take outside, and now we have by squared into dy. The moment d2 C also must have the same value, so the dead moment is m is given by m is equal to m, that is er is equal to 2 into 0 to d by 2 by squared dy. Therefore m is equal to E by r into 2 into 0 to d by 2 into y squared into b dy, which is equal to E by r into 2 into 0 to d by 2 into y squared dA. B into dy becomes dA. Now you see that 2 into 0 to d by 2 y squared dA is actually the second moment of the area of the cross section about the neutral axis, that is called as moment of inertia I. Hence m is equal to E by EI divided by r, and therefore the equation becomes m by I is equal to E by r, so which is nothing but m by I is equal to sigma by y is equal to E by r. So this is the final our required equation of simple bending theory. Okay, so let us see some of the assumptions that we should follow in this simple bending. The material is linear elastic isotropic and has the same elastic properties in tension and compression. The beam has either zero curvature or very small initial curvature. It bends to a circular constant curvature arc. So these are all some assumptions. The radius of curvature is large compared to the depth of beam. Cross section of the beam which are plane before bending remain plane after bending. The beam bends about a principal axis. It is symmetrical about the other principal axis. Stresses are induced only along the longitudinal fibers. The beam shear is absent or is ignored. Deformation due to shear are not taken into account. Local effects such as those due to support reactions and concentrated loads are not accounted for. So because the shear is taken as 0 and the moment due to reaction force, everything is being eliminated because the beams are subjecting constant moment. Constant moment means there will not be any shear. Okay, there will not be any shear, and therefore we are neglecting these all factors. Once if we neglect these all factors, that is shear is absent and the moments due to reaction force is simply not accounted. So once if we have done these all things, then only we get the constant moment acting on the throughout this section. So for that we just took this kind of assumptions. Then significance of them. When the material is non-linear or inelastic, the strain equation 4.1 is still valid, but the stress equation 4.2 will need modification. So for that we just use this kind of assumption. Assumption 4 restricts us to beam that have a span to depth ratio exceeding 10. For deeper beams, the plane section assumption has been found to be inapplicable. Even so, it is customary to apply equation 4.4 for span to depth as allow us 3. Okay, so because if span to depth ratio is merely gets reduced means, so here the shear will be predominant, and therefore it has some limitations. The derivation of equation 4.5 were ostensibly made for rectangular section, but the same is applicable to all symmetrical sections shown in figure 4.7. So now we must use only the symmetrical section for this case. At least any one of them should be symmetrical about y axis. These all sections are symmetrical about y axis. So the beam should have this kind of cross section in once if we use the simple bending theory equation. In most practical problems, the engineer analyzing a bending moment wants to whether the maximum bending stress induced in a beam due to given bending moment is safe. Hence, the extreme fiber stresses are particularly important, because that fiber stresses only are subjecting maximum bending stress, because the as per the bending relation theory, simple theory maintenance, m by I is equal to sigma by y. So in case of sigma bt is equal to m by I into y bt, therefore sigma bt is directly proportional to y bt. What is y? Y is nothing but the distance between fiber distance and the neutral axis. So if we y is maximum only the distance between neutral axis and the extreme fiber. So in that case we have obtained the maximum. Suppose if we take a particular section, it is subjecting a constant bending moment. For the given section, I is constant, so sigma bt is only varying with respect to the y. So the y is the maximum distance, that is the maximum extreme fiber. So if we want to find the stress at extreme fiber, so then only we get the maximum neutral axis, that is y distance. Okay, y distance is nothing but the distance between neutral axis and the extreme fiber for this case, so that we will obtain the maximum fiber stress. Zb is nothing but I divided by yb. Zt is equal to I divided by yt, and z is equal to I by y max. So these are the how can we find the section modulus for this case. Some of the formula that we can use for the moduli of section, that is section modulus for the different shapes. In case of rectangular section, we have I is equal to bdq by 12, and y is equal to d by 2, yt and yb is also always equal, and therefore zb is bd square by 6 and zt is equal to bd by 6. But in case of rectangular, you see that yb is d by 3 and yt is equal to 2d by 3, and therefore I is bdq by 36. Then zb is 1 by 12 bd squared, whereas zt is 1 by 24 bd squared. Okay, but in case of circle all are constant, and therefore we will obtain the zb is equal to zt is equal to pi dq by 32. So like here the rectangular hollow rectangular sections, we have d by 2, and zt zb are also constant because these are all symmetrical section. So in case of hollow circular section, we have the same formula because it is symmetrical section. So by using these all conditions, we can see a problem for this case. A steel flat of size 6 mm into 40 mm into 2000 mm is bent in the form of an arc of radius 4 meter. Its E value is 2 into 10 power 5 into. The yield strength of steel is 400 into. Check the stress induced due to bending. Check if there is any yielding. So now this is the maximum stress that the arc that steel flat, maximum stress that the steel flat can be subjected. You see that when it bends like this, whether it is we are going to find out its fiber stress. So we know that epsilon b is equal to minus d by 2 divided by r. Here the radius is given, the arc of radius is given, therefore minus d by 2 divided by r. So here d by 2 is minus 3 thickness, and r is it is given 4000 mm, we obtain epsilon b, bending strain is like this, then sigma b is equal to Young's modulus into that value, we just put 1 foot into 1 square, but the yield strength is 400, therefore now the flat is in more safe, like that we can check. So this is the another problem, again it shows the same concept. So these are some problems that we can use the same concept. Let us see one more problem. In this case, simply about a timber beam of span 6 meter. It carries uniform distributed load of 20 kN per meter run over the entire span, and a point load of 15 kN at 3.5 meter from the right support. Now we are going to design a suitable section for the beam, making the depth of the beam as twice its width. The bending stress in timber is not exceed 7.8 Newton per ohm square. So these are all the data given. Now you see that span of the beam is 6 meter. UDL load is given 20 kN per meter. Again a point load is also given. Depth of the beam is 2 times width of the beam. D is equal to 2B. Maximum bending stress is also given. So first let us find, our aim is to find where the maximum bending moment subjected. So I think it is obviously actually we must find that one first. As usual, first we find the reaction Ra and Rb, in which we just formulate the equilibrium equation taking moment about B, sigma mb equal to 0, therefore Ra into 6, since it is clockwise plus, and minus 20 into 6 into 6 by 2, this is moment due to external load, and it is anti-clockwise, therefore minus, and minus 15 into 3.5, this is moment due to point load with respect to B. Finally Ra we just obtained 68.5. Rb is equal to total load minus Ra, it is 66.25. the shear force is assumed to change sign in portion CB. Actually the shear force, we get the maximum bending moment at which where the shear force changes its sign. So first let us find the where the shear force changes at its sign. So for that here they are assuming the shear force's sign changes in between C and B in this portion, and therefore let us take that distance a section XX. With respect to left support, let it be x, and therefore we just formulate the equation, shear equation. So this is the x, this is the left up Ra plus, and this is left down loads, therefore minus 20 into x. Up to this section there is downward UDL 20 into x, and there is downward vertical force, and it is minus 15, which is equal to 0. Now the x becomes 2.688, from which from A it is 2.688, so it is away from C. Definitely it is away from C. So first we have to guess where would the maximum shear subject, where the shear force changes its sign. So under this point the maximum bending moment that we can apply. Now maximum bending moment will occur at 2.688 meter from A. Yes. So maximum bending moment M is equal to, now let us find at that section, that is 2.688 from support A. So for that we just find Ra into 2.688, this is sagging moment, therefore we put sign positive, that is moment due to reactive force, minus 20 into 2.688 into 2.688 by 2, this bending moment is hogging, therefore it is put minus sign, because due to external UDL load, and again minus another UDL load, we just find the bending moment at that section as 109.727 kN meter. This is the maximum bending moment at that section. Now at this section, what is the maximum bending stress subjected? It is given directly, from which now our aim is to find the size of the section, and therefore we know that Z is equal to BD squared by 6. B is 2 times, D is 2 times B, substitute, and we get Z in terms of B, like that. We know that M is equal to sigma into Z. So because this thing can be found by using the relation m by I is equal to sigma by y. Now m by sigma is equal to I by y, that is z, and therefore m is equal to sigma into z. So from which we have this relation. Now m, the maximum bending moment, has been found in this case as 109.727 kN meter. So it is being converted as Newton mm by multiplying with the 10 power 6, which is equal to 7.8 into sigma. That value is given 7.8, and z value is 2b cube by 3. Now b cube that we got, from which we know that relation d is equal to p 2b, and therefore b from which we can find d is equal to 560 mm. Now this is the size of the beam required. So like that we can design by knowing these all values. Yes, next chapter let us see the flitched beams. What is flitched beam? Another method of making beams more efficient than rectangular beam is to provide a weaker material inside and a stronger material as the extremes. So as we have already seen, that is with respect to neutral axis the stress becomes 0, and the adjacent fibers of the neutral axis also subjecting lesser bending stresses, and therefore we can concentrate the weakest material at a nearby the neutral axis, whereas the stronger material can concentrate only at the extreme fibers. So in that concept we have the flitched beams. Here the under stressed regions have a cheaper, weaker and lighter material. The highly stressed extreme have steel. These generally prove to be more cost effective than plain steel or timber beam. Stresses in composite beams. Composite beams, as we saw already, we have seen these all things in the in this previous video lecture, that is in the unit number 1 videos lecture, in which have more than one material. They are likely to have different values of E. We can proceed with the assumption that the two materials are bonded together and that there is no slip between them. This is the same as concluding that at the interface of the strains are equal. For example, in the figure 4.15, say epsilon t is equal to epsilon s at the interface fiber. That is, epsilon t means strain at timber, which should be equal to strain at steel. Yes, this leads us to sigma s equal to es into epsilon s, sigma t is equal to et into sigma t. Now sigma s by sigma t, which is equal to es by et, which is nothing but the modular ratio, and hence sigma s equal to m into sigma t. Okay, for example, if es equal to 2 into 10 power 5, et is equal to 4 into 10 power, then m is equal to 5, and therefore sigma s equal to 5 times sigma t. So now the problem can be dealt within either of two ways. One is by considering the stress diagram to be like in figure 4.15c, or by considering an imaginary equivalent timber beam where the width of steel is increased in m times. So like that we can find. So let us have a small problem. A flitched beam. So before that, a flitched beam consists of a wooden member strengthened by two steel plates shown in figure 4.25. The maximum stress in wooden joist is limited to 7 megapascal. Find the corresponding maximum stress attained by steel. Also find the moment of resistance the composite section. Take E steel is equal to 2 into 10 power 5 MPa. Then E wood 1 into 10 power 4 MPa. So with the wooden member, it is given 120 mm. Depth of wooden member, it is given 240 mm. Width of one steel plate is 10 mm. The depth of steel plate, that will be 240 mm. Allowable stress in wood, it is 7 MPa. E for steel and E for wood. So this all the data have been given. Moment of inertia of wooden joist about neutral axis. Let us find I. I is equal to it is the formula is I is equal to BDQ by 12, and this is for wooden joist, that is inside the material. Then moment inertia of two steel plate at its end about neutral axis is, that is 2 into BDQ by 12, is equal to 2 into BDQ by 12. New molar ratio m between, now molar ratio m between steel and wood is ES by EW, it would be 20. The equivalent moment of inertia IC can be given by I is equal to m into IS plus IW. Therefore, we will just find equivalent molar ratio IE with the use of this relation. And moment of resistance of the composite section is MR is equal to sigma W divided by Y into IE. We just find these things. This is the moment of resistance of composite section by using this relation, that is m by I is equal to sigma by Y. And therefore, from which we can find the moment of resistance. Maximum stress in steel sigma S is obtained from sigma S equal to m into sigma W. We know that is sigma W, and from which we can find sigma S for steel. Now the moment of resistance of the composite section is equal to 40 into 40.32 into 10 power 3 Newton meter. Maximum stress in steel 140 into per square. These two data have been obtained from this relation. That's all. Okay, using the flitted beam concept, once by knowing this M and MR, we just find this sigma S and the what is the moment of resistance on the composite section. So next, let us see the shear stresses. Another very important, we have so far we have discussed about the bending stresses, how the bending stresses can be calculated by using the simple bending theory equation. So next, let us see the how do we find out the shear stresses on beams. Another very important aspect of behavior of beams, namely the importance of shear stresses between layers in a beam. If two flats are simply kept one over another, they bend independently, and when they are secured together, they act integrally. So the various layers in a beam need to be secured to each other so that they can resist the shear displacement by developing shear stresses on the horizontal plane. These layers must be shear connectors. Yes, you see that this is the individual flats. If it is not integrally connected, so there will be a shear displacement. If it is integrally connected, the shear displacement is arrested. Like that, in this beam, this shear displacement has been arrested, and therefore shearing resistance is produced. So, so there is an element of length dx of a beam subject to a varying bending moment. Let the bending moment vary from 0 at the left end to dm at the right end. Hence, the shear force W is dm by dx. Yes. Here the m equal to 0, and here m plus dm. So the bending moment dm will cause a stress distribution at the right side at any level y. The stress is sigma x equal to dm y by I. Yes, of course, we know that sigma by I is equal to m by sigma by y is equal to m by I. Thus, therefore, dm by I into y. This is the stress developed due to the excess moment dm. Let us look at equilibrium of slice A, B, D, C. On the left, there is no bending moment, so no sigma x stress. On the right side, we have sigma x forces varying as shown. This net force must be balanced by the horizontal shear Q on the face CD. If the shear resistance is absent, the element ABDC would slide horizontally to the left. The equilibrium condition for ABDC yields our equation. We see that B dxq, this is nothing but shear force, and that is slice, and it which is equal to y1 integration of y1 to y2 sigma x into b dy, which is equal to integration of y1 to y2 sigma x is nothing but dmy divided by I, and beta into dy. Okay. Therefore, q is equal to dm by dx. q is equal to dm by dx into 1 divided by ib into beta y into dy. So F divided by ib, dm by dx is nothing but shear force. F divided by ib into y1 to y2 is equal to beta y into dy. So that's all. That is the shearing equation for the given section. Okay, where beta is nothing but the sheared area of that particular section, a sheared portion. So in this equation is the famous shear stress equation. It gives the horizontal shear at any level, any flexural member. Here F is the beam. F is the beam shear force that we talked about in chapter 3. Q is the shear stress at some height y1 from the neutral axis. y1 does not directly enter the equation. B is the beam width at level y1. This can be constant or varying. Integration of beta y dy is the moment of the shaded area of cross section of the beam above the level y1 of the about neutral axis. Integration of beta y dy can also be written as a y bar, where a is the shaded area. So y bar is the distance of the centroid of the shaded area about the neutral axis. Hence q is equal to f a y bar divided by ib. So what they have given, integration of beta y dy can also be written as a into y bar, where a is the shaded area. Shaded area means at which fiber we would like to find the shear stress, and the above fibers have been considered. Okay, so the area above that fiber which has been considered as a, okay, that is called a shaded area. And y bar is nothing but the distance of the centroid of that shaded area and the neutral axis. The y bar is the distance of centroid of the shaded area about the neutral axis. Hence q becomes f a y bar divided by ib. So this is the very important equation to find the shear stress on the individual fibers of the beam. That means if we want to find the shear stress at any fiber, suppose I want to know the shear stress at this fiber, and therefore I have to find the sheared area about this portion, and the y should be substituted that above center of that point to the neutral axis distance, that should be taken as y. Yes. So let us know this is q is equal to f a y bar by v2, and this so now we can find the shear stress for the different sections. Okay, so you see that let this is the sheared area portion and that distance be u. Now the area of the sheared area becomes u into the breadth of section B. U is nothing but from the central axis distance it should be d by 2 minus y1. What is y1? y1 is the distance of neutral axis and the bottom area, or at which the fiber that we need to find the shear stress. Okay, therefore this u can be written as from d by 2 is the center of the beam minus d by 2 minus d by 2 minus y1. Yes, that will be the depth of the sheared area u. Yes, therefore y bar is equal to y1 plus u2. Yes, the y bar is, so this one be the y bar. Y bar is nothing but centroid of the sheared area, distance between centroid of the sheared area and the neutral axis. It should be y1 plus u by 2. So I is equal to 1 by 12 bd cube. Therefore q is equal to f divided by ib into this It is FA y bar. A is shade area UB. Y bar is from the net loss that one should be y1 plus u by 2 divided by FA y bar divided by I into B. Now F divided by I into in which B cancelled, therefore u into y1 plus u by 2, therefore q is equal to F by I into u into d by 2 minus u plus u by 2. So finally the equation becomes F into u of d minus u divided by I and by 2 or 2I. So q is equal to, we can form F into u into d minus u divided by 2I. So this equation gives the variation of q in rectangular beam section, and this is parabolic in u and q. Yes. So because by multiplying this u, that is the distance of fiber at which the shear stress can be found, or the shared area of depth. So when it is multiplied with in this section, it becomes u squared. Therefore we are obtaining the parabolic variation of the stress distribution. So q is the maximum when dq by du is equal to 0. So d minus 2u equal to 0. Q is maximum at u is equal to d by 2. So let us use substitute in this equation dq by du, and therefore we have d minus 2u equal to 0, therefore u is equal to d by 2. The distribution of shear stress q is shown in figure 4.32. We find that the shear force is not taken by the cross section uniformly as q is equal to F by A, but in parabolic distribution having zero stresses at top and bottom and maximum stresses at neutral axis for rectangular section. So we just substitute this all things in this rectangular section, because in this rectangular section u becomes d by 2, and therefore we have q max is becomes F by 1.5 F by BD. By substitute these all things in this equation, just in this equation u becomes d by 2, and therefore it becomes F divided by 2 into I. This is d minus d by 2. Okay. So already u outside, d by 2 into d by 2, it becomes d by 2 whole square, and therefore F by 2 into I is BDQ by 12. Okay. So I is at the bottom, therefore 12 by BD cube, which is equal to d squared by 4, and therefore we have 1.5 F divided by BD. Okay. Therefore Q average is F by BD, that is shear force divided by whole area of the cross section. Now Q max divided by Q average becomes 1.5. So like that we can find the shear stresses for different stresses. That is maximum shear stress and the ratio between maximum shear stress and average stresses for circular section, triangular section. That thing can also be found. Now a beam of rectangular cross section 150 mm width and 350 mm depth is subjected to a shearing force of 100 kN. Calculate the maximum shear stress. So the data is given. F shear force is 100 kN, therefore 100 into 1000 Newton, which is B is equal to 150 mm, D is equal to 350 mm. They are asking maximum shear stress, which is equal to 1.5 times F by BD. So substitute these all things, we can find the Q max. So for the given rectangular cross section. Okay. Yes. So with this, I just conclude the this chapter. Let us see some other chapters in the next video lectures. Thank you.